automatically be able to share screen? Will Xiao-Li automatically be able to share his screen, or do I have to do something?
And
okay,
I guess I need to share the screen.
Okay, let me introduce you first. Well, you start sharing the screen while I introduce you.
Sure.
We'll operate together. Okay, welcome to the first foundational lecture of ISBA 2021, featuring Xiao-Li Meng. Since we are doing this electronically, answering questions during the talk is not really feasible. Hopefully there will be time at the end for Xiao-Li to answer questions. Xiao-Li announces on the ISBA webpage that his current position is founding editor-in-chief, Harvard Data Science. I think he's also still a distinguished professor at Harvard, but today he just wants to be an editor. Foundational lectures are supposed to be for newer researchers, but everyone loves them because they're usually understandable. Whatever definition you give to foundations, Xiao-Li qualifies. He has been a part of so many foundational advances scientifically that I would have to spend most of his lecture just outlining them. Interestingly, he is not dwelling on any of his older foundational advances today, but is gifting us with a new one. He's talking about Bayesian inference with incomplete likelihood of prior, employing quick and dirty Bayes theorems, and prior impact assessments. Xiao-Li, it's all yours.
Thank you so much, Jim. And well, you know, I feel great honor to be invited to give a foundation lecture. I thought hard about what does exactly foundation means. And in the end, I thought, you know, maybe nothing's more foundational than talking about the Bayes theorem itself. And it just happened I've been doing some hopefully interesting work most recently. So I want to share with you on that. And the talk is really combining two articles. One is about dealing with Bayes when you have an incomplete likelihood in a special case. So it turned out to be quite interesting. The other is another older topic, probably as foundational as possible, is about checking the prior assessment. Now, I do have a request for at least one of the organizers. I need to see a face. I need to see some face before I can give a talk. I can see some reactions. Otherwise, it's very hard for me. So maybe Minghui or Jim, that if you don't mind to share your face with me, that'd be great. Jim, sorry, that I just put you back. I want to start the talk by invite you to listen to a kind of a interesting radio show. I don't know if you can hear it. Let me play this to see if Jimmy, you can give me a reaction if you can hear the audio.
Hi, we're back. You're listening to Car Talk with us, Click and Clack, the Tappert brothers, and we're here to talk.
Okay, so what I'm going to invite you to listen to a short piece from a popular radio show called Car Talk. And I was driving to a dentist. This is I think it was July 11, 2015. And suddenly they start talking about this thing. I said, wait a minute, that's a public kind of a example about the Bayes theorem. I got very curious. What did they do, and did they do it right? And in the end, this actually leads to an interesting, Bayes, what I call dirty Bayes theorem, which I did not know, and probably is not news to many of you. But since there's a foundational lecture, as Jim said, I'm trying to be as basic as possible. So I want you listen to this talk show. Essentially, they post this called a puzzler, and I will stop in the middle. Then we'll play again. Okay.
Talk about cars, car repair, and the answer to last week's puzzler. This was the final puzzler of the current puzzler season.
So I should savor this one. It's going to be a doozy, isn't it? A real season-ending splash? Is it going to be as good as the mango tree?
Jerk.
All right.
There's a rare disease sweeping through your town and the disease is called ACI, and it produces irreversible anal cranial inversion. You may have noticed that my brother has it. Now, of all people exposed to ACI, only 0.1% actually contract it.
Ah.
Okay, a tenth
0.1%.
A tenth of a percent. Okay.
0.001.
And if you catch it early before the symptoms present, you can get treatment and maybe you can be cured. Fortunately, there's a diagnostic test which can detect ACI up to a year before the inversion occurs. So anyway, you go to your doctor and he administers the test and it comes out positive.
Yeah.
And you say, oh, I'm done for. Then you get a little bit encouraged. You say, wait a minute, doc, is this test 100% accurate? And he says, well, not really, but it's 95% accurate.
95% accurate.
Right? In other words, 5% of the people who take the test will test positive, but they don't really have it. The question is, what are the chances that you will actually have an irreversible anal cranial inversion? And the answer is...
All right. So you can clearly see this is like, a Bayes theorem, except that when you listen to it, you say, wait a minute, and how would they get the answer? Because they tells you the preference rate is 1 out of 1,000. And then they say that the accuracy is 95%. Now, Ray, this host, interpret that 95% as a false, actually, I always get this wrong. This is the sensitivity, right? This is if you have the disease, what's the chance you will be actually, test positive? But you will get the false positive rate, but you never get you will never get the false negative rate. And so the question is like, how do they actually do this? Because you have a piece of information. But let's listen to.
You worked out the math yet?
No, I haven't.
It's reasoning. Okay.
Well, let's do it this way.
Go ahead.
What did I say? The rate is 0.1%?
Yeah.
Okay, so 0.1% of the people who are exposed would actually get it. That's 1 in 1,000. Is that right? Mm-hmm. Now, you tested positive, and you figure I'm done for, especially when you find out the test is 95% accurate. But if it is 95% accurate, that means if 1,000 people take the test, 50 people who don't have the disease will test positive, right?
Let me see now.
Well, let's make it simple for you.
95%. Yes.
Let's say if it was 100 people who took it. Let's start here, Tommy. 100 people.
No, I'm with you. I was on a different track. I'm with you. 50 people who take the test will test positive, and yet they will not have
right.
it.
So I have 1,000 people who take it.
Yeah.
Okay, and you're included in that 1,000.
Yes.
Okay, 51 people out of 1,000 are going to test positive. One of those people is going to have it, and 50 are not going to have it.
Correct.
So your chances of actually having it, even though you tested positive, are 1 in 51, or a little less than 2%.
2%.
And that's just another way that statistics can fool you and lie to you and make you jump suicidal and jump off a bridge. Because you tested positive.
Sure.
And the test is 95% accurate.
Sounds so good. So you're saying 2% is pretty small.
Well, I mean, your chances of having it are 20-fold greater than just a person off the street.
Exactly. Right. Which is only 0.1%.
By testing positive.
Yeah.
But it's still, I mean, considering how dire the news was just a moment ago.
Now down to 2%.
Down to 2%. I mean,
don't even pay any attention.
I mean, you got a 2% chance of being hit by Skylab. Is that still up there? Anyway, yeah. Who's our winner?
The winner is no kidding.
Jeez.
What are the chances of?
Anyway, so you get the sense. This is it was fascinating to me because this clearly was a kind of Bayesian reasoning gets played out in a popular radio show. And the question I hope that all of you start thinking about is this correct, right? Okay. So this is basically the first part of my talk. Now let me stop sharing that. I'm going to start sharing my slides. Thank you for one of. The person reminds me I was sharing the entire screen. I actually did that intentionally because I want to make sure that the audio actually works. But now I'm going to only share this this screening. And so let me see if I can do that correctly. This online thing is still, after 1.5 years, we're still not doing great in terms. Okay, now I'm going to share the screen. Okay, so you have heard that particular, talk. Can you see, Jim, can you see the slides? Okay, great. All right, so what I want to talk to you about is that this reasoning is clearly, cannot possibly be correct because it only used the one one of the two rates, right? You need the specificity, sensitivity, or you need a false positive or the false negative, but they only have one number. But somehow they got this kind of a magic, a formula, and seems incredibly simple. And the question so got me very interested in is to see, okay, where this reasoning come from, and how good was that answer? And that's essentially turned out to be a part of the article I'm actually writing for this new journal, which I'm advertising here. It's the New England Journal of Statistics and Data Science, and Ming Hui is one of the a co-chair editor. And I have to say that I'm still submitting the article, and so, but this is just to remind people that there is this new journal coming out. And the second part is really about dealing with the price situation, the assessing the price impact. It's an article that just got published by JSP with Matt Reimherr and Dan Nicole. Okay, so it's really a two-part. One part is about likelihood, and one part is about the price. So let's just review what this talk puzzler did, right? It tells you that its preference is 1 out of 1,000. And it says that the doctor says the test is 95% accurate. Now, for most people, that sounds like a good enough, right? 95% accurate. Now, as a statistician, we all started asking, oh, wait, 95%, what does that even mean, right? So, we have at least 3 different measures. There's a sensitivity, right? It's the, given the disease is, you have the disease, what's the probability the test is positive? You have a specificity, right? Given that you don't have the disease, what's the probability the test is negative as well? And you also have this overall accuracy, which is the test, it is the same as your disease status, right? Whether you have it, it tests positive. If you don't, you test negative. And it's very easy to see that it's the weighted average of the sensitivity and specificity using the prevalence as the weight, right? So at least you have these 3 choices here. And so initially when I heard Ray was talking, I said, wait a minute, how would they even get right? Because they don't have the information. But it's a squarely a case of, incomplete likelihood, right? You have some information, but you don't have all the information to, specify everything. Now, clearly that whoever posed this puzzler, or maybe Ray himself, that they didn't even think about the sensitivity specificity, right? For Ray, the way he said, oh, that means 95% accurate. That means for people who have, if 1,000 people who don't have, who don't have the disease, that the 50% of them will be, will be positive. So so he was I think I might even, this is always a problem that, oh yeah, this is correct. This is hence the error rate, right? Is a false, false negative is 5%. So what he did is this a remarkable formula, which is very simple to do. You can do it in your head, right? Even doing the regular base, even for us as a professionals, thinking about sensitivity, specificity, even you get it right, the preference, trying to come up with a number immediately is not that easy, okay? But in this one is incredibly simple, right? What he said is, well, take a preference and divide by the preference plus the false negative rate, and that is 1 out of 1 out of 51. 1 out of 51. That's, he said it roughly is 2%. Okay. So sorry, I was keep saying the false negative. I might be actually, this is the problem. Even for me that I always get this wrong. It should be the false positive rate, right? Because it's the for people who don't have the disease, that then you will. Okay, so I will correct that later if I do need to correct it. And so the question is this a correct answer? Clearly no, but is it a useful answer? Well, it turned out to be, it is very useful because it's actually quite close to the true answer for the rare disease, right? And this is, 1 out of 1,000 is relatively rare. So what's the reasoning here? Well, if we write down the Bayes theorem, right, we can easily write down as this, right? What's the probability? So this is the full Bayes theorem. And I think I was actually correct. This is F. This is a false negative for 1 minus F. For the, that's a sensitive. This is too hard for me. that's the sensitivity here. Okay. So when I look at the formula, I say, okay, how did he get that a simple answer? And what's the reasoning here? Well, if you take the correct base answer divided by 1 minus, false negative rate, if you look at this, and you will see that the correct base is less equal to the number that rate give, if and only if the preference rate is less than the false negative rate, right? Because this one will be bigger than 1. Okay. So what he derived here is, if you think about it, he's saying, okay, if I don't really know what the false negative rate, what false negative rate is, as long as I know the preference rate is low enough, is lower than the false negative rate, then using this very simple formula is a quick, it's an upper bound. And for this kind of assessment, probably the upper bound is really good enough, right? And in this case, that you can do the calculation if you're assuming that false negative rate is also 5%. That the exact answer is 1.86, and this answer is 1.96. It's 1.87. This is 1.96. So it's not that different, right? And what's interesting here is this bound. If you can actually just do the calculation, you will see this bound is actually quite good overall, as long as the false positive and the false negative rate are not too high. Now, hopefully, the medical test, these rates are not too high. Because if you look at overall, this is regardless of where the P is, it's bounded above by these two quantities, so essentially controlled by both the false positive and the false negative. So as long as false positive, false negative is not too large. For example, usually probably say 10%. If you have a false negative rate of 10%, then this is about 11% the relative errors, right? Regardless of where where P is. And for lots of practical situations, again, but this particular case, if this is a real situation, does the doctor or the patient really care if it's 1.96 or 1.87? That's pretty much come to the same conclusion, right? It's unlikely the person has disease. Now, it's not like the difference between say 2% and 20%. That makes quite a big difference. So this is a great situation where essentially that by understanding how this formula works, that you can derive these useful bounds that not only they are quick to calculate, and actually since I learned this, now I can really, for lots of situations, I can quickly calculate in my mind, say roughly what the answer is, right? You will be impressed when people say, oh, it's about 2%, and to do the exact calculation again, takes a little bit of work. So this essentially, I don't know if Ray comes to a conclusion by doing this calculation, which I doubt. He might be actually really misreasoned, but approximately correct, right? Because for the kind of positiveness, that false negative rate itself, plays less, less a role. But what was a little bit surprised to me is that what if that Ray's interpretation, that 95% rate was not the false positive rate? Was not the sensitivity, but rather was the overall accuracy. And that part really surprised me. Now, I did a little bit calculation. Now, again, this results may not be new at all, and particularly Jim can tell me. And but I thought it was quite interesting that. So I played it with the idea, if I replace F plus, which is was a false positive rate, by the overall error, right? The overall error here is, if I can move my slides. Come on. Okay. So the overall error rate here is simply what's the probability the test does not equal to the disease status. It's a 1 minus overall the overall error rate, overall accuracy, and then you can show, right, the base answer. Once you test the positive, what's the chance you really have it? Is less than or equals to this simple bound, incredibly simple, right? P over P plus the overall, if and only if F is less than the overall accuracy rate. And you can also show that the overall error rate, the relative error in this approximation is entirely controlled by false negative rate. And And there's also this one, actually, I still don't quite understand why that works. And in fact, there is one result that I thought it was incredibly simple. It must be telling something, but I don't have a great intuition for it. And again, I hope Jim can tell me if it's very intuitive. It says that this Bayesian answer about whether you have disease or not is a tau causing if and only if the preference rate equals to the overall test error. Right? It's a very neat one. I mean, you can see from here. If F0 equal to FO equal to P, this is half because it's if and only if it goes both ways. So it said that if you test of a disease, and what's the chance you have it? You actually have a coin tossing. If it happens, the overall accuracy of the test is exactly the prevalence rate. Now, why is that? Why there's such a neat answer? I don't have any good intuition, and I'm hoping some audience will tell me. Okay, and so once I did that, I get it slightly carried away. And then I say, no, what if I only know false negative rate instead of false positive? Do I still get some quick bound? Now you can see that if I'm asking what's the probability that if I test positive, then I really have disease, the false negative rate is not going to tell me much. I mean, it has some information. But in this case, you can actually play a different kinds of bounds, and that might be useful. And it turned out to be another interesting, instead of now bounding the false negative, false positive rate with the preference, this is essentially saying that you can write, if you only have one of the rate, as long as these false positive, false negative rate are not too far from each other, you can use one to substitute the other. Then essentially balance is given by these ratios of odds. Well, ratio of the odds ratio essentially. And again, if this case, if you're trying to do the overall control, the relative errors is really controlled by the difference between the false positive and the false negative, and divided by the false positive rate. Now, this, I want to say this one is not very useful, but again, I just put it out there since I trying to complete it, and it might be useful that in lots of medical test situations, the doctor might know that the false positive may be roughly 10%, the other may be roughly 5%. There may or may not be too far, that get you something going, that these are like a ballpark estimate of these these base risks. Again, we're talking about dealing with this incomplete situation, right? Now, here are the plots just to show you that when this is given 4 different scenarios of the pairing of the false positive and false negative rate. One, both are 5% and both are 1%. Sorry, 5% or both are 10%. In those cases that as I show you that if you replace false positive by false negative, because that's exact, you will see that the black line is the original base answer, and all the other lines are these bounds. And the bounds can go up and go down, depends on where the P is, right? Remember, we talk about there is a cutoff point, but the point here is that these bounds are not too bad, and except I think the one can be really bad is the one based on false negative, because I'm really doing the false positive, trying to get the positive rate. And here are the overall performance in terms of relative scale, in terms of the delta. Delta essentially is the relative difference compared to the original truth. And you will see that for the particular case of this is the truth again, is the black line, and in this case that the plus and the minus is on the dot, because both false negative are equal. And the other rates are, remember, this range is kind of misleading. Here you're really talking about only the relative error is about 4%, and here the relative error is about 5% on the original scale. And these are slightly off, and the ones that are really off, as I said, is using the false negative rate. And I don't really recommend that, but it's kind of more for completeness. But if you use the other two, use either the overall rate or you use the false positive rate, you get the answers are really, for practical purpose, are really quite good. You're off by at most 10%. So the point I want to do this very quick illustration about the other situation, might be the simplest situation, because we have binary outcome, we have these very simple situation. But it's very interesting that how this kind of thing can help the public to understand these are Bayes theorems. It's not exactly right, but for most people, at least to get them to say, wow, the answer is not 95%, near 95%. It's a very quick way of getting something as close to what we will teach people to do. And if you tell the public you need the false positive, false negative, and the preference, you probably lost them. But this one is, again, incredibly simple. Take the preference, divided by preference plus the error rate, and either the false positive or the overall overall error rate. So I certainly invite people to think more about this kind of a dirty base and see if in other situations we can get this kind of quick assessment that is for practical purpose is very useful, but it also has kind of a pedagogical value. Now that's all about the likelihood part, and I now want to switch to talk about this pry issue. Well, for the pry, as we know, right, anyone who has really done the real pry calculation, the pry knowledge is always incomplete. I was going to put down almost surely always incomplete. I said no, forget it. I have just never seen a place where you truly have the information for you to specify the whole distribution. So what do we do, right? We basically do. What we do is that we will try to put down something we know, and the rest we're trying to make some kind of a non-informative guess or trying to be flat, right? But whatever it is, I think it's very important for us as a responsible analyst or responsible base that we should at least have a rough idea about the impact of the pry, right? Especially the made up part, like the part we don't really know, but we need the full pry to get things going. So we say, well, let's assume something quite innocent, right? If you're doing, for example, if you're doing covariance, let's say, take a common like inverse Wishart, you do something quite like everybody else does. But nevertheless, I think we need to really know to quantify in a way like, how much impact is really made by this type of, despite the pry. And we want to assess pry here, and many of you and many of you in the audience, and certainly Jim himself, that have done lots of works that, assessing the pry information is not easy at all, right? And in fact that we because one of the difficulties, there's no such like truly ignorant pry, so you can do a pry with respect to that. So it's common in the literature that you always think about, like you take some baseline pry, and in this case, say, here's the pry that we're not making any big assumptions, and here is a pry we make more assumptions, and to see how much additional impact that new pry that you care about will make. But the other thing is also quite well understood is that when you assess pry, you need to think about assess the pry relative to the likelihood, right? And in particular, you need to deal with this issue that the pry and the likelihood may or may not go together. There is this kind of a conflict between the pry and the likelihood, and that's probably is one of the thorny issues in the literature that has leads to a lot of articles. I want to mention that this article, as I said, has just come out of the JRSB after literally about 10 years work. And I tell you, initially when we submitted this article, the reactions, particularly from, I think it was a particular referee, I think it was Biometrica. We obviously got rejected by Biometrica. I think it was a hardline frequentist, and basically said, why are Bayesian still working on these problems assessing the pry? Like, should you have done this thing before you promote the Bayes? Like, you guys have no idea how much impact is made of pry. Like, why do you work on this problem? So it was really took a while for us to convince people that this is still very much important problem to work on. I will tell you a little bit about the literature. So let me just say what we're trying to do here. Again, there's a lot of pieces you will see. Many of you say, well, that sounds really, really familiar, and you will be right. What we're doing here is really trying to convert the pry information into something called a pry sample size, right? Try to equivalent the pry to a previous study. So there's really not new here. And the old notion of the conjugated family, you can really do that in a very analytical way. And here we're trying to do it before the conjugated family. The other thing we do, as I already hinted, we try to formulate the pry sample size, not as absolute notion, but a relative to the likelihood sample size. Like, what is relative to the sample size, and what is the prior sample size. So you will see that our prior sample size varies as a function of the likelihood sample size. The other thing I think, this might be, if we have made any contribution, this might be a slight contribution, that we really permit a negative sample size. Now you will say, well, what do you mean by negative sample size? How could a sample size be negative? Well, here is that what we're saying is that when you have a prior likelihood conflict, you can actually, assuming the prior, to make your inference worse in terms, say, the standard mean square errors, in terms of your estimate, because the prior literally takes away the sample size from the likelihood because this conflict. Not all conflicts are harmful, but some conflicts will be harmful. And we will have a specific notion. So that's where we actually was able to get additivity, because we allow this kind of negative, negative sample size. In this case, the way we formed it, you will see actually make a real, make a real sense. Okay. So what are the connections to previous work? There are really tons of them, and my apology to many of you that if I did not list here, you read the article, we list them all, but I'm sure we have missed quite a bit, right? This idea of matching the data and the prior is not new at all, right? There's others working on that. Using the base prior, this Evans work about assessing the what they call the base, the surprise index. It's all based on these base prior. Then Jim, Bernardo, does a lot of these reference priors, is very much related. And you can use a deviance information criteria itself is a kind of indicate of the the amount of information, relative price, surprise, as already mentioned. As recent as just a couple of years ago, you have works on using historical data to quantify the prior impact. So we're saying that, again, I want to emphasize that if you read our article, you will find pieces here, there's are really already in the literature, and we just put them together in a particular way, and we hope that is useful. And I think the part might be new. I will show you that there is a asymptotic formula to tell you what the prior sample size is when in a kind of specific setting. Okay, so again, like the first part, it's a kind of a quick and dirty assessment. So what's a general setup of what we're trying to do here? We're really trying to do the following. We're trying to assess the prior sample size as specific to the prior data, the data you have as possible. There are lots of prior sample size assessment in the literature is kind of a design-based. It's talking about average over all the data, what would be the prior sample size. We're trying to be a little bit more specific. Now, on the other hand, as you know, we can't fully condition on the data we have, because then, if you condition everything is fixed, there's nothing to talk about. There's not even a way to measure information, right? Information requires variation. Everything is fixed. You can't even talk about this this information. So what we're trying to do is kind of utilizing this notion of using the data, because data coming from the underlying truths, trying to estimate things from the data itself, so therefore to be approximately is relevant for the particular data you have. So the notion itself is not a fully Bayesian notion, because it's not fully conditioned on that particular sample size the data you have. So let's take a scalar quantity. It's an information index or impact index. If you have ID data, then the sample size itself is a very good indicator. But the formulation we have does not really require it to be just you can take any kind of indicator index you want. We require a dispersion measure. Again, it could be variance, mean absolute deviation, mean square errors. We're trying to be very practical. Say, assessing information, on the other hand, it would be very difficult, right? Because information is always about for what question you are answering, for what specific problem you have. So we basically say, okay, let's say you have a specific criteria in mind. Let's say posterior mean square errors or sampling mean square errors. Whatever you have. So this is a criteria you have. And what we're trying to do is we're going to take the average is with respect to the posterior. This is our way of trying to be as conditioning as possible. Even there is a little bit averaging, going on, because we don't know what the theta zero is, right? The theta zero is the one generate generate that particular data set. So what we do here is, as I said, we assuming a baseline measure, and again we cannot get rid of that, and we got quite a bit of criticized by the reviewers. Say, well, you're still assessing prior with respect to a baseline. Can you get rid of that? It turned out to be you really can't, and at least we don't know how, just because of this whole notion of there's no way to putting a prior is truly ignorant. And what we do here is a very simple notion. What we just say, okay, we say, suppose the prior you care about, this is your uncertainty measure, thinking about your posterior variance or mean square errors, whatever it is. This is what you can achieve. Now, assuming the baseline is kind of weaker, right? So you need the more information. So we're saying, what will be the effective sample size? Like how much information I need to add to the likelihood so that this uncertainty and this baseline measure will be the same as the uncertainty and your measure, your prior, right? So the idea here is saying, no, typically you are thinking about adding the sample size. You're saying this was the original, think about I here is the sample size. This was the original likelihood sample size. What additional how many more data points I need to put in to make my inference and this baseline prior same as the accuracy or the precision I can get and the prior I care about. And this basically tells me, like, relative to this prior, the baseline prior, is how many more the sample size, the prior is worthy this many sample size. Okay? And of course, in this formulation, you can see m can be negative, because if it turned out that your inference here actually gets worse than the baseline prior. But of course, it cannot be worse than more than taking away the entire sample size. It could go down as much as like 0, like you lost all the data, right? So what we do here is we say that what we find is the following, that then we basically using this for any sample size. Think about I here is a k. For any sample size, we numerically solve for this number, and we plot this number against the k, and k here is the sample size, k from 1 to 3, to n, to whatever sample size you have. And then what we found that if there's a serious prior and likelihood discordance, this kind of conflict, you will see this effective prior sample size will be going down, and eventually gets wiped out, because essentially that the likelihood is going to take over. The worst case scenario is that this m can reach a slope to -1. In fact, you can actually show this. This is kind of interesting. You take a derivative with respect to both sides, pretend this I is continuous, and then you can show that this derivative m is equals to, by the kind of the chain rule, equal to this side. Now, as long as your uncertainty measure itself is monotone in decrease as the sample size goes up, so its derivative is positive, you will see this side is positive, right? And many measures, if you choose well, they do monotone decrease as you increase the sample size. So this shows you that the worst case scenario essentially is you have a -1, a 45-degree line, that kind of negative slope. And but on the other hand, that if the likelihood and the prior are really what we call it, concordant, then the prior sample size pretty much stayed as a constant, and as it should be, because if you have a previous study is kind of exchangeable with the current study, then whatever the previous study sample size is going to add to the current study, so the sample size will remain pretty much constant. The reason you see its decrease is because your prior is in conflict with with your likelihood. So because the way we design it, right? Because the way we design this way, we have the identity by design. The information in the posterior equal to information in the likelihood prior plus the information in the prior, or maybe you want to call it impact if you don't want to call it information.
Excuse me. But the only reason we can get such a neat identity many others cannot get is because we define this way. The price you pay for it, maybe that's a feature, not even price, that you need to allow the price impact to be negative. Because otherwise, there's no way this can hold, right? Because we know the posterior inference can be worse than the likelihood inference, especially if you do the kind of frequentist evaluation, right? The only reason this can hold is because by this definition, because we allow this to be negative. So now let's using the normal example to illustrate like what this tells us, and I call this called a normal alignment because the normal as usual tells us a lot, and in fact later when we do the posterior approximation using the large sample, this normality kicks in, but it requires a particular kind of sort of asymptotics, as I will talk about in a minute. So let's say that we use the conjugated phi, and assuming the 1 over m, essentially thinking about the m is the phi sample size. Then let this delta is essentially what the phi z statistic is talking, is the prime mean minus the truth and divided by its standard deviation. So you essentially have this delta quantity. This delta quantity is crucial, essentially measuring how far away is my prime location to the truth in terms of the prime prime standard deviation, right? And then if we use the mean square error as the measure, then you can easily calculate, right? And under the baseline measure, which is because we're using conjugated phi, at the baseline measure, which is m goes to m goes to infinity, you get m go to 0. M go to 0, you will get 2 over k, and otherwise you will get this quantity for whatever the pi for whatever pi sample size is m, and the k here is the likelihood size. As I said, we define this in terms of likelihood size. So once you do that, you can actually calculate what is, if you solve for this thing, right? And R here is the pi sample size over the likelihood sample size. Remember, here we're using a kind of a generic likelihood sample size. K equals to from 1 to n. N is what you really observe because we want to plot this entire curve. You will get this formula. It's a very handy formula. It tells you the effective sample size relative to the likelihood sample size equal to the m. M here is the original sample size, pi sample size you kind of put down. And then you have this factor, okay? This factor looks like it's going to be, depends on what the delta is, positive, negative. It could be above 1, above 1 or below 1. But what's interesting here is that initially I thought what will make the pi sample size is exactly m. It will be like if the prime mean is equal to the truth. Well, that turned out to be really not the case, because that would be really, you will be too lucky, right? So it turned out that depending on this formula that you will have the following scenario, okay? That if the delta square is less than 1, delta square less than 1 is saying that you're actually pretty close to the truth. If you set the pi such that is essentially within kind of 1 standard deviation, right, of your pi variance. So that's kind of the kind of a lucky situation. Then your effective pi sample size is actually more than what you think, right? Because you're 1 over m. M is your is nominal pi sample size. So you will have more. But what's interesting is it also has an upper bound. Now, this upper bound, I still don't quite understand where these numbers come from. The upper bound here varies from 1.5 to 2. The upper bound will be, it basically says that no matter how lucky you are, you can never be more than twice of your pi sample size as you declare. So that's the kind of lucky situation. And the next situation is essentially what we call a concordant. Concordant is the case that when delta equals to 1, right? Delta equals to 1. If you look at this thing, this actually makes quite a big sense. Basically saying that your prime mean is essentially set as exactly one standard deviation in terms of prior standard deviation from the mean. Essentially, like your z statistics is, z chi-square, right? A chi-square, z square is a chi-square with 1 degree freedom. So its expectation is 1. So basically saying that if you really the z statistic is right on the mark for prior z statistic is 1, then what you announce to the prior sample size is exactly what you get. Okay, so that's a special case. Now, then you have this unlucky case, right? But what if the delta square is larger than 1? Basically saying that your prime variance, the standard deviation you set was actually a little bit too optimistic, that you're away from the truth more than one standard deviation. Then you get into a situation that it requires further analysis, because if first said it will reduce your prior sample size, but worse, it can make your prior sample size negative. So now I'm going to look at this situation into 3 cases. The first case is you are unlucky, but it's still helpful, right? The first case that if the delta square is less than this mysterious number, but it's less than, if it's delta square is not too large, it's still less than 3 plus 2r, then you still maintain your prior sample size is positive, which means that your prior still helps you. It still make your likelihood the sample size goes up. It just doesn't go as much as n as you think, like according to your price specification should go up to, okay? Now, there's also this case, which again, I don't have intuition why 3 plus 2r. Maybe there's an interpretation here. And this is what we call zero impact prior. Basically saying in this case, if you do the base, if the delta square equal to that, you did the base inference, but in terms at least the posterior mode, that it's exactly same as the likelihood MLE, at least in terms its variance or mean square errors. So you're basically saying in this kind of a frequent this mean square error, this kind of evaluation, your prior did nothing. It's a zero impact one. But the worst one is this one, and this is what we call the really harmful ones, right? When delta square is bigger than 3 plus 2r, this is in this normal case, then you really have a harmful situation if you care about your variance of your point estimate. You did the base estimator, but in fact, in terms of its mean square error again or variance, that it's actually really less than if you just did the likelihood, if you just did MLE. And that's because that's where we start, because that's where things is essentially saying there is a conflict between the prior. The prior is getting quite far away from the truth, and we're still assuming the likelihood is correct in this case. Okay, there's a far more complicated. What if the likelihood itself is wrong, right? Then that's another further complications, because then you can have situations 2 wrongs may even get you right. But here is at least the likelihood is right. If the likelihood is right, this mu pi is essentially the mu 0 kind of captures where the data location is. So if the prior gets too far away, and then it starts to distract you from. So this is the theoretical calculation. Of course, in practice, you can't really do this exact calculation. So what we did is there are 2 ways to implement this. One is do the asymptotic calculation, and it turned out to be this formula is also asymptotically correct as long as you can estimate the delta from the posterior quantity. And the other is do the kind of if you have ID data, you can estimate this thing almost like doing bootstrap. So this is a way to implement it. If you have ID data, we still need to work on the non-ID data in terms of implementation. Essentially, you're basically, because once you can estimate these quantity, remember we were doing this kind of a posterior expectation, not really posterior expectation, it's a posterior predictive expectation given the truth. So therefore, that if you do the bootstrap sample and every time you take a bootstrap, then you run the Bayes inference, right? You do the 2 Bayes inference, and you can calculate both the mu's, one uncertainty and the other is and the baseline. So this is computationally very intensive, but you can do it, right? You can numerically do it. Then you can numerically solving how many sample size I need to add into these 2 quantity. In practice, of course, you don't get exactly equal, but you minimize their difference. So again, I want to emphasize computationally this is very, very intensive, and but you can do it. There's nothing stopping you actually doing it. You'll be starting probably, you don't want to start from k equal to 1 because the likelihood that the base, everything gets just so unstable. You can start with a k reasonably large. You do that, but you also don't want to get too close to the end. The asymptotic theory tells you that these a good approximation, because we don't know what the theta 0 is. We need to approximate it by using the theta n bar, using all the data. In order to that to be a relatively a good estimator, whatever anything else you do should not be too close to that. So there is a asymptotic will tell you, I'll show you in a second, that your k should not exceed square root of n. Of course, this always makes trouble for practitioners. Like, what do you mean by square root of n? Because there's always a coefficient, but we literally kind of take square root of n. There's a choice of the d's. You can using the variance, you can use the bias. We did a variance thing because of time constraint. I'm not going to go to detail, but in all the things I'm illustrating next is simply using the mean square errors. Okay, so this is a case that essentially just kind of a test of the proof of concept. We all obviously know how to do it, theoretically calculate, but we also did the simulation just to see how the simulation works. Everything goes as as the intuition suggests. So in this case, we choose a different kind of the choose is 1, and the variance is all equal to 1, and the sample size is 1,000, and we choose the prime mean equal to right on the dot, and 2 equal 3, and the price sample size we choose just like 4. And you will see that when you choose that price sample size equals to when the delta equals to 1, that's where this m is flat. This is, remember, the m equal to 4. This is the case that no matter what you plot as k is, that's pretty much flat, as the theory suggests, because it's essentially in this case saying the pi and the likelihood are completely kind of concurrent. Therefore, the price sample size starts the same. Anything else, you will start seeing a little bit of a negative slope. Although the most extreme negative slope comes when the delta is pretty far, right? In this case, the choose is 1, and the prime mean is set as like a 3, and the standard deviation is only standard deviation here is the variance is the standard deviation here is a 0.5. This is like 4 standard deviation away. So now you can see that these, when you do a plot, it's telling you that this is this is negative. What this minus 0.5 means essentially is saying for every basically saying that for every sample size you put in, the pi is taking away 50% of the sample size. So basically saying the pi in this case cut off your likelihood by half, because it's set up so far away. Now let's look at a real situation to see how this is being actually used. This was a study I actually did a long time ago, but it turned out to be simple enough to illustrate this. That this was a logistic regression case to trying to estimate a particular kind of a pretty nasty kidney disease based on these 2 predictors that are based on these 2 predictors through the medical test to predict whether you have this kind of lupus. And in this case, you probably, someone with a sharp eye, you can see it's almost like a nearly separable cases, because most cases are here and there's not much here. So the likelihood, if you fit the logistic regression, these betas tend to be, the posterior is trying to be almost like a nearly non-identifiable. And we use this example to illustrate this whole concept of, Andrew Gelman has this concept called the weakly informative pi, right? And he suggests a particular pi, Cauchy pi, for these logistic regression. In this case that he recommended you standardize covariance to have mean 0 and a variance 1/4. And he used the Cauchy with scale 1,000, Gelman used the Cauchy with scale was 10, which is already pretty spread. But for our purpose, we set up a default pry using Cauchy, which is already pretty heavy tail, but with a scale parameter 1,000. So that's a really almost like a flat line, but not exact, right? And then we try to test a variety of the different scales. One of them is recommended by Gelman, which is 2.5. And he assumed that 2.5 will lead to a kind of weakly informative pry. And we want to know, like, what does he mean by weakly informative? Does weakly informative means that the pry impact is 2% of the whole posterior, or 10%, or 20%, right? So we use this example trying to figure out how informative or weakly informative is the Cauchy pry with scale 2.5. We also check with the Cauchy scale, say 1,000, and we set the baseline again, very wide. Essentially, it's like constant pry with scale, 10,000. So here's what we did. We just implement that Monte Carlo, that bootstrap way of doing it. And here you will see that the thing varies quite a bit. And as we increase the sample size, remember the whole sample size is n equal to 55. So we didn't start from 1. You actually requires like 6, 7 data points, because otherwise the logistic regression itself is very unstable. And we basically say putting like a random choose 10, random choose 12 from that data set, and then calculate what that price sample size is. And you will see those things are going down. This black line is when the scale parameter is 2.5, and the red line is the scale parameter is 5, and this green is scale parameter is 10. So as you using the scale parameter larger and larger, you will see that the sample size is getting closer and closer to being, because remember we took the baseline is really huge, right? The baseline was 10,000, but whatever it is, right? So it gives us a comfort, like basically, and the thing after a while start to be kind of a asymptote, and you can't go too far because we only have 55 data points. But what this shows is that what Gelman suggested, the 2.5 scale parameter, is equivalent to about a sample size. The price sample size is about somewhere between 2 and 6, right? Now, for this purpose, I think it's good enough. We don't really care whether it's really 3 or 4, 5. Basically, it's said the impact of the pry, that it is kind of weak. It's about 10% of the, so this posterior inference, whatever the posterior, at least in terms of the point estimate, the posterior mean or posterior mode there, it's mean square errors that about a 10% of that is that the reduction in this mean square error there, that the 10% of that is contributed by the pry, right? So we were saying in this case, I think we can, if we tell people this is a weakly informal pry, it is useful to have that kind of numbers to say, maybe 10, if you give yourself a little bit of a wiki room, the room here, you might think about is something between maybe 10 to 15% of the contribution to the inference, to the posterior inference, is coming from pry. So that's essentially is what we try to do using this tool. And here comes the theorem, and I really should have stopped. The theorem is essentially trying to justify that asymptotic formula, and but there's one thing essentially what we did is we assuming the pry mean pry variance. Say there is a way to you can find a pry location. It doesn't have to be pry mean, and such that essentially your pry distribution, the posterior can be written is in this what we call a functional kind of shrinkage estimator. There is a shrinkage factor, essentially this is a weighted average like the normal case, but you can have a function on top of that. And we verify that for many kind of a problems, this kind of requirement is not strong. Certainly holds for all the conjugated family. So we have looked at. But the key thing is to do this asymptotic calculation. There is a key assumption, which is that the assumption here is that you cannot just let the n goes to, you cannot let the sample size go to infinity and fix the n. Because if you let the sample size go to infinity, then the pry gets wiped out, right? Because as we know that if you have a fixed pry, if your likelihood to n go to infinity, there's no asymptotics you can work out can show that kind of inferential pry. in order to make the inferential pri, the pri needs to stay. And when you show the how inferential pri is, the pri needs to stay relatively strong with respect to the likelihood. So the asymptotics we did is to keep the delta, which is the pri z statistics, as fixed. You can move the sample size, you can move everything else. Essentially saying that we look at the sequence of the problems where the pri location is equal distance to the likely location in terms of pri study precision. And that's just a asymptotic game, and it's useful for this purpose. And with that, you can show the formula I show you holds to the order of square root of k. That's why you can't have the n k goes beyond the square root of n. There is a mysterious number called the c here in the general formulation, but for most applications, c equals to 2. And that's in the normal case equal to 2. In general, what the c is the ratio of the sampling variance of the posterior mean divided by the posterior variance. Now, asymptotically, the sampling variance of the posterior mean and the posterior variance are always equals to half of that. So that's the quantity is essentially is you can calculate in most cases essentially is a quarter. So the formula I give in general, as long as these assumption holds, that you can use that as a quick or dirty approximations to calculate, and without doing that a bootstrap. So let me just wrap up in terms of future work. There's a lot of future work, right? The MK does not exist if your pri is so strong that it is stronger than the likelihood itself. Then obviously the impact will be huge. We cannot use the one methods. What about dependent data and high dimension parameter? We kind of work on these kind of low dimension problems. Computationally, if you do the bootstrap, is a grand challenge. And in the implementation for small k is quite unstable. We choose a different form of the D's. There are many things we can work on. But I hope I give a little bit of introduction here in terms of this kind of thinking, trying to quantify the pri impact specifically with respect to likelihood and with respect to the particular problems, problem you're working on. And here are all the references that I mentioned. And thank you very much.
Thank you very much, Xiao-Li. Very nice talk. I think the screen defaulted for me because we went over the hour-long time.
Sorry about that. Yeah.
No problem. There were a couple questions. I think we're about to lose the session, so probably no time to answer the questions. But you can maybe look at them and answer them offline.
Okay.
So thank you again for a wonderful talk, Xiao-Li.
Thank you. Let me see if I can.